Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, welcome Microsoft regulars and our new visitors who've come from, in some cases, great distances. So thank you for being here. And thank you for your willingness to teach us in a very rapid tutorial that Matthias and Krysta have scheduled about your respective subjects. I think it's probably correct to say that Microsoft is the largest curiosity-driven research institution in the world, Microsoft Research. And once our curiosity has taken us to some place, it's our tradition to understand the real-world implications and see what's out there. And in the case of quantum computing, we do have a very strong and long-standing history of curiosity research in this area for over 10 years. And in particular, with this project, we're very interested in the real-world applications. How does the theoretical acceleration of certain problems translate into real-world applications? So, in a nutshell, what will quantum computers be able to do best if and when they're built? Now, many of you come from disciplines where perhaps you don't think of yourselves as quantum computer scientists. But I want to reassure you that anyone who does quantum mechanics professionally for a living is in a very good position to discover and design quantum algorithms. I think you do not need to be familiar with the formalism, which the next talk will explain, of quantum circuit model. So I don't think you need to think in terms of pictures like this, for example. It's too small to read, and I don't read this language anyway. And I'd like to give you some evidence for this. And the evidence is that very interesting ideas, you might call them breakthroughs in thinking about quantum algorithms, have historically, in many instances, come with their own model. People who know quantum mechanics and understand some aspect of it think of something that quantum mechanics could do, and later on, people translate that into the quantum circuit model, into pictures like that. But the initial inspiration may come with its own design. For example, the idea of using quantum computers to solve logical problems, satisfiability problems, max cut problems, things like that, problems that are technically NP hard. We don't expect to be able to solve them in polynomial time, but it's possible that quantum computers can give some interesting speed up, perhaps a square root in the exponential, who knows, over classical algorithms. And the idea here was introduced initially by Svore, Goldstone, and Gutman, and it, as most of you know, it was to initialize a Hamiltonian so that the ground state solved a rather trivial problem, like finding the ground state of a ferromagnet, and then evolving the Hamiltonian slowly so that the solution tracked in the ground state. It's a problematic proposal, and it has to do with the size of the spectral gaps, how well it'll work. But it's an idea that just required knowing the adiabatic theorem. It didn't require knowing what a quantum circuit model was. Another example from the same group, actually, is using scattering theory. You can think of it as a quantum rather than a random walk in a tree. You send wave packets, perhaps of light, through some kind of optical tree. And depending on how you've designed the tree, the transmission probabilities can tell you something about solutions to game theoretic problems, such as values of a NAND tree. And again, this was within a week translated into the quantum circuit model, but the idea just came from knowing scattering theory. And a third example is from Aronson's work. It's actually with a graduate student, Arkhipov, whose name I should have included. And this is based on the old joke that in quantum mechanics, bosons have the much harder time of it than fermions. because free fermion systems, the ground state will be Slater determinant. And we know from a computer science point of view that determinants are polynomial, very easy to compute. And it's one of the great achievements in complexity theory, theorem from 1979 of Valiant, that permanence, which is the positive version of determinants, this is where all the alternating signs are just forgotten and become plus signs, that those are sharply hard to compute. So the fact that the ground state of free bosonic systems will tell you something about permanence is kind of a wedge into a new way of thinking about quantum computing, a new architecture. It's not a complete slam dunk from that statement, because the thing you have to always think about in quantum complexity is that quantum computers are probabilistic machines in terms of their output. So just knowing that an exact solution is extremely difficult does not necessarily tell you that an approximate solution conveys a lot of computational power. So that's why this paper of Aronson and Arkhipov is 95 pages long instead of 2. You have to analyze the error. And this Hong Au Mandel dip, this is like a 2-photon experiment that originally shows the correlations that they proposed building a machine to exploit. So I'm actually not saying, and I wouldn't assert, that any of these 3 ideas are practical. I mean, I don't know. I think they're all interesting open questions. But it's just evidence that, if you know quantum mechanics and you have problems to solve, you may think of ways of using quantum mechanics, and they may really be out in left field with respect to the way quantum computer scientists are trained, to write down algorithms. So there's a big cadre of people that will turn your idea into an algorithm if you have a good idea. So roughly speaking, the proposed applications of quantum mechanics seem to lie in 3 large baskets, you might say, of increasing murkiness. So the sharp and clear applications are the very mathematical ones, finding units in a number field, factoring numbers, discrete logarithm, things like this. These tend to be algorithms that you can analyze their computational costs, prove fairly sharp bounds on their efficiency. And it's not this kind of thing where you need a lot of real-world experience to learn how well these things work. Now, people have proposed using quantum computers for simulation and design of quantum mechanical systems, nanostructures, maybe going way beyond the Hubbard models to studying cuprates, things like that. And that's the kind of thing where one really has to start doing the numbers and seeing whether it's realistic or far-fetched, given the resources we're likely to have in quantum computing. And I'd say that maybe the third category is probably closest to the kinds of applications where you'd expect experience to be essential rather than theory. So to figure out how important quantum computers are going to be in these areas, like general optimization and machine learning problems, it's probable that we need a quantum computer and we have to interact with it and learn gradually. It lacks sort of the mathematical crispness, in my opinion. But that's not to say that maybe some insights can't be gained early. So I'd like to sort of finish by showing you 2 slides I recently gave. I gave a public lecture last month at the Salve Institute in Brussels. And this is sort of typical of the way public lectures on quantum computing either begin or end. In this case, was the way mine ended. So it's full of all these kind of bold assertions, somewhat shaky, some caveats about, what things we know how to do and where we might look for areas that classical methods have trouble with. Then I went on to list even the more speculative applications. And then I got a little modest and said, well, we don't really know. But my goal for this meeting is to get past those first sentences, at least in one narrow area. I'll be very happy if, after we're done tomorrow, I can say sentences 2 through 10 about one of those subjects. Thank you.
Okay. Well, thank you everyone for coming, and thanks Mike for our motivation and introduction for our meeting. I'm Krysta Svore, and I'm a member of the QuArC group, the Quantum Architectures and Computation group here at MSR in Redmond. And because we're coming from different backgrounds, some of us are more on the classical side, some of us are on more of the quantum computing side, I thought I'd give just a very brief, this is a 15-minute introduction to the quantum circuit model and how we think about quantum algorithms in that language, and a really brief introduction to phase estimation, which is one of the key hammers in our toolbox that we would use for quantum algorithms potentially in this space in materials and chemistry. So I wanted to start just by introducing you to our group members. Sorry, Alan, I couldn't find a picture last night. We're a new group. We're about a year old here in MSR Redmond. And for those of you, obviously I know the Microsoft people know us, but for those of you who are new and outside, external to Microsoft, we have a new group here in quantum computation. And we're a sister group to Station Q, and we focus more on the computer science, the quantum circuits, quantum algorithms, and Station Q focuses more on the theoretical physics. So I think we're a good team. And here's our members. So if you see them floating around, the bottom group of folks are consultants and our key collaborators. So. And our group focuses on designing quantum algorithms, so that's definitely one of the reasons for having this meeting. And we like to think about the implementation on small, medium, and large-scale quantum computers. So what would we do with hundreds of qubits, thousands, and then maybe millions? And then we think, as Mike said, you don't need to know quantum circuit or how it'll be implemented on the quantum device to design a quantum algorithm. So our group thinks about the quantum algorithms, but then we think about taking an algorithmic idea and actually converting it down to the device specifics. So we think about programming languages, optimizing the quantum circuit, converting the Hamiltonian into a quantum circuit that's going to be efficient, and questions like this. And then finally, in support of that goal of breaking down the algorithm into the device components and the device operations, we're building out a full comprehensive system architecture that will help in designing and programming a scalable and, of course, fault-tolerant quantum computer. And tomorrow, you'll have a great tutorial on Liquid. And the Liquid is our architecture, our platform for programming and simulating quantum algorithms and quantum circuits, and also Hamiltonians. So that will be tomorrow morning, and Dave Wecker here will be giving that then. So in an introduction to that, I'll introduce some of the language, and then he'll show you how you can take this language and these tools and actually use it to program or simulate something. So to start with, I know all of us know quantum mechanics, so I'm going to try to just take quantum mechanics and then just translate it into what we do for in the quantum computing and the quantum circuit model. So with a qubit, naturally a qubit, it lives in a two-dimensional complex vector space that has an inner product, so it lives in a Hilbert space. And we can think of these two, for example, these two vectors form an orthonormal basis. So we typically think, we call this the Z basis. And in the quantum circuit model, we typically write everything in the Z basis. So the state vectors then are just 1, 0 for the 0 state, and then the vector 0, 1 if we're talking about the 1 state. So in general, we can write any qubit, any two-dimensional quantum state here as a general linear superposition of these two basis states. And so then the vector we use is alpha beta. where the alpha and beta are the amplitudes, and alpha and beta are always complex numbers. And of course, they have to satisfy the normalization condition. So then we can think about if we move to multiple qubits, the size of that state space. And so, for example, a 2-qubit state, we have now the superposition over 4 possible basis vectors. And again, we have all of their amplitudes, and we again have to satisfy the normalization condition that the sum of the amplitudes squared has to equal 1. And then we can, of course, move to a bigger state, so where we have n qubits. And again, it's a linear superposition over all of those orthonormal basis states. And again, it satisfies the normalization condition. I'm sure this is all repeat. So then let's think about the quantum evolution of this state, this system. So from quantum mechanics, we know that the time evolution of a closed system is going to evolve following Schrödinger's equation. So here's Schrödinger's equation, which we all know and love. And then we want to talk about how we can express this. And we know that we can solve Schrödinger's equation for 2 time points, t1, t2. So we want to know how the state space evolves between time t1 and time t2. And so we start, with our state psi, our quantum state at time t1, and it evolves as a unitary evolution, a unitary transformation u. And we can see the relation between, if we define u to be e to the ih, the difference between the times over h bar, then we can see that the unitary evolution of the system matches the continuous time dynamics of Schrödinger's equation. So this is where you come up with the Hamiltonian, and then we want to actually find what the unitary is. And so this can be challenging, finding an efficient unitary that computes what we want, that computes this evolution. So in general, we want to know what these unitaries are and which ones we can use in practice and on the device. And in general, a unitary can be written, any unitary can be written as u equals e to the ik, where k is some Hermitian. So what unitaries are natural to consider when we actually want to build this device and make efficient quantum algorithms? So here are a few that we use in practice. Very common. So for single qubit operators, so unitaries act on just a single qubit. The typical ones we know, from quantum mechanics and physics, of course, we have the poly operators. So the poly gates, in physics we refer to them often as the sigma I, sigma x, sigma y, sigma z. In the quantum circuit language, we often just call them I, x, y, or z. And so we have the identity, the x operator. So x operator is a not. We call it not in traditional computer science language. The not operator takes the 0 state, converts it to a 1 state, and a 1 state and converts it to the 0 state. And that's defined here by this 2x2 matrix. And then for the other 2 poly operators, we have sigma y, and then we have sigma z. Sigma z changes the phase, and then sigma y is a combination of x and z, so it does a bit flip and a phase flip with also this additional phase I. So we use these all the time in our quantum circuits. And then we, of course, have a phase gate. So if we want to think about applying an arbitrary phase theta to our quantum state, then we can do this with a rotation about the z-axis by theta, by angle theta. So in general, then, the matrix is defined as 1, 0, 0 e to the I theta, where theta is the angle about which we're rotating around the z-axis. So we all know the block sphere picture. So here, the 0 state sits at the north pole, the 1 state sits at the south pole, and then here's the z-axis. So when we talk about a phase gate, it's rotating there about the z-axis by angle theta. And there's some common z rotation gates that we use a lot. The first being, we've already seen the poly-z operator. This is, in fact, a z rotation where theta is the angle pi. And the S gate, which is called the phase gate, the S gate is 1, 0, 0, I. This is just where theta is now pi over 2. So it's, again, a rotation about z. And then finally, a very important gate, the T gate, which we call the pi over 8 gate, but theta equals pi over 4. So here, this is a rotation by angle pi over 4 about the z-axis. We call it the pi over 8 gate because you can factor out, in this form, 1, 0, 0, e to the I pi over 4. If we factor out e to the I pi over 8, then you'll be left with pi over 8s on the diagonal. So it's called the pi over 8 gate. And this is an important gate because for to have a universal single qubit set, we require something outside the Clifford group. So all of these gates, the Pauli gates, are in the Clifford group, plus one more gate. The Hadamard gate is in the Clifford group. And this is not a universal set, the Clifford group. So we have to add an additional gate, and that's the T gate. One candidate is the T gate, which allows us to implement any single qubit unitary in practice. So the final gate to mention is the Hadamard gate. And this gate is given by 1, 1, 1 minus 1 plus this normalization. And this gate allows you to perform a superposition. So you can take the state 0 to 0 plus 1 over root 2 and the state 1 to 0 minus 1 over root 2. And now we can start introducing some quantum circuit diagrams. It's the smallest one in this so far. So normally we denote the gate as a box just with the name of the gate inside of it. And then this represents, the wire is the qubit. So this represents applying the Hadamard gate to whatever the state of the wire is, to state psi. So then we can move to 2-qubit operators. And the most common 2-qubit operator is probably the controlled NOT gate. So this is a controlled X gate. And what this gate does is it takes, so we have, it's a 2-qubit gate, so we have qubits A and qubit B. And it takes qubit A and qubit B to A and the XOR of A and B. So essentially, it says if my first qubit is 0, I don't do anything to my second qubit. If my first qubit is 1, then I'm going to apply the X operation to my second qubit. And so the matrix here, you can see that in the lower right corner, we have the X gate. And in the upper left corner, we have the identity. So in general, if we want to apply any controlled U, which comes up a lot in the quantum chemistry algorithms, we have to apply a controlled phase gate. Then if it's a single qubit phase, for example, we would have the identity here, and then that U or that phase gate sitting in the bottom right. So we now can construct any controlled unitary operation. And the diagram for the controlled NOT is this here, where this is the control line. So if this qubit is 1, then we apply this. And that's the symbol for, well, it's the XOR, which is why we're using it here. But you also might see a controlled with an X in a box on the bottom qubit line, which would match this notation here. So this is the notation for any controlled unitary operator U. And again, the filled in circle means that qubit has to be in the state 1 for it to be applied. Another gate that comes up is the swap gate. Swap gate simply flips the state of the 2 qubits. So AB goes to BA. And this can be, for example, it can be implemented with a sequence of 3 controlled NOT gates. And the unitary is given by this matrix here. So if you can solve this, and you can see that if you do 3 controlled NOTs, where the middle one is in the opposite direction, then you will see that you have a swap gate. So feel free to matrix multiply away. You can solve that. And then the notation is often these two x's with a line in between to say we're swapping the state of those two qubits. So that's a quick introduction to all of the quantum gates, most of the quantum gates we use. And then I want to just go through and introduce phase estimation, because I think this is going to come up in maybe a lot of the talks today. And so I think we all know this well, but in terms of the circuit notation we use, which you're going to see a lot of tomorrow in Dave's talk and maybe some in Matthias's talk, or maybe not. Definitely in Dave's talk. This will give you an idea of how we think about it in more of a computer science circuit way. So this is one of the, or maybe the most common subroutine. Grover's a candidate as well, of course. But between Grover and phase estimation, those are our two main tools for designing quantum algorithms. We'd love to have more, so we should all be thinking about that, of course. But these are good things to look at when you're thinking about a quantum algorithm. So in the phase estimation problem, we have some unitary u, and then we have an eigenvector psi, eigenvector of u, and the eigenvalue of this is e to the 2 pi I phi. So that's, u psi equals e to the 2 pi I phi psi. And the question we have when we're doing phase estimation is we don't know this phi value here. And so we want to say, can we get an estimate on what phi is and to what precision? So we want to estimate this value phi. And there's a way, a known circuit to do this. And there's actually several known circuits. I'm presenting one. And there are different circuits that don't use some of these gates here that you can do more classical processing. And we can talk about that separately. But here I'm just going to introduce one of probably the most standard that most people see in the textbooks. So here's the quantum circuit for performing phase estimation. So we start with a bunch of qubits all initialized to the 0 state. And then we have our eigenvector psi. So already one of the assumptions of this subroutine is that you can prepare psi in some efficient way. That's not always possible, of course. So we want to think about algorithms where we can actually prepare psi efficiently. And then, so we have then a large superposition state here in the top register. So we refer often to a set of qubits as a register, as we would in more traditional computer science. So this register is going to be controlling the application of these unitaries. So what happens is now these are in a large superposition. So part of that state, or one part of the basis states that are in these superposition are going to get the u's applied to them, and the other one won't. So then we have a sequence of powers of u, controlled powers of u. And then we're going to apply the Fourier transform. So what happens just at this state in the computation, after we've performed all of these controlled u operations, the different qubits, the different wires here, contain the following states. So at this point, this qubit is in the state 0 plus e to the 2 pi I 2 to the 0 phi 1, and so on down to 2 to the n minus 1 phi. So you can see where this is starting to give you, if you can extract this information about the phase here, you can get information about the different bits. So you can get different precision or accuracy on the estimate of phi. So what we're trying to do is get information about each bit of phi basically here. And how do we get that out? Well, we know another trick. We can use the quantum Fourier transform. In this case, we use the inverse of the quantum Fourier transform. And what does that do? So this large box here has a bunch of gates going on inside of it, which I'm not reviewing in this talk, but we can. But it's a straightforward, efficient quantum circuit. It's polynomial time, actually quadratic. So we can. What this box does is it takes this state, which is the state of the system at this point, and it's going to map it to this estimated version of phi, and then it leaves our state psi, our eigenstate, our eigenvector, it leaves it alone. So the algorithm, yeah.
Slide. What is that little slash with an M next to it?
Oh, that's saying, sorry. Yeah, so in the circuit model, we often do this to denote that this is an m qubit state.
Oh, okay.
So this register has m qubits. This register has, some other number of qubits based on what accuracy you need.
I'll add in this example.
I think the two are unrelated.
Yeah, we have we have n qubits in this register and m qubits in this register in this diagram. Yeah. And so if we were to just look, so in an algorithmic, if we were to write this out as an actual algorithm, then the input, we require a black box or a quantum circuit that's going to allow us to perform controlled U to the J operations. So depending on the efficiency of this could be an efficient method or not. We require the ability to prepare this eigenvector psi. And then we also need some number where this is going to be set based on how accurate and how often we want. So based on two things, how accurate we want our estimate of phi to be, and then also how often we want it to succeed.
Just the thing, the n in this slide is not the same as the n in the prior slide.
Oh, I probably switched notation, sorry.
The n is the thing on the right, the log of 2 plus 1 over 2 epsilon. That's the number.
Oh, I think I flipped some stuff around. Sorry. Okay, and then, I changed the letter again. This should be M, I think. Sorry about that. Okay, so then the output is an approximation to phi. And then the runtime of this, the QFT takes n squared time, where n is now my n here. And the oracle, and then it's plus the cost of this black box, this oracle. So I'm saying we can apply this, controlled U to the J. If we can do that efficiently, then that's the cost.
There's no F15 in quantum computing?
Yeah, so you can do a little better than this, I think, in some implementations of the. We do have, yes. So you can do an approximate. Well, you're asking about the fast break.
The fast break wrong.
Yeah, but this is
Still n squared?
no, because the n here is different. N here is log n.
No, n is.
Oh, right.
Yeah.
Yeah, sorry about that. We're in the quantum. Yeah. And then let's see. So we have some success probability as well that we use. The algorithm will succeed with some probability of success, and we can set that, increase the number of qubits if we want it to succeed more often, for example. And then the procedure. So as we saw in the circuit, as we write this down in an algorithm, we would say we start with 2 quantum registers. This register, according to this slide, contains n qubits. And then psi has m. And then that means after we perform the Hadamard gate, which we saw on the previous slide, then that takes us to a superposition over all the states, plus our original eigenvector psi. And then we undergo this black box, this U to the J.
So when you say 60 probability, one way. Second, the source of failures is when so where is the randomness coming? Is the source of failure?
So we measure. All quantum algorithms are probabilistic. So here we're measuring. We're measuring this state. And so there's a chance we're going to measure the state, the zero. If we measure the zero here, let me go back one more. Let's say when we measure, imagine we're measuring this state, for example. There's a chance we're going to measure a 0, and we don't get any information. So it's the measurement that has the probability associated with it.
So Krysta,
I maybe should show it here, actually.
I think
Because we're measuring
I agree with
this.
Krysta, but I think the thing which is interesting is you have basically this real number which you're truncating to an integer, and that bottom, the very last part of it, like that is a random choice. If you pick the wrong one, then your thing crashes.
Yeah, so every bit that we're trying to approximate has a probability associated with it. We're not always exactly in this to the end, this ring. So we're not going to get exactly every bit with we're not actually always going to get the 0 or 1 bit exactly. So we have a probability associated with each bit.
Let me just try to answer Yuval's question. I think the error comes from a mismatch of two discretizations. If you had n qubits in those top registers, and that phase phi was had a k over n in the denominator, then there'd be no source of error. But the problem is you're doing a discrete Fourier transform, trying to detect a unit complex number, which is not necessarily in that cyclic group. So the Fourier transform won't be completely a delta function. And then the end of the quantum computation is you sample the Fourier transform with respect to the norm squared. So you will be off a little bit.
Right. Yeah, I should have probably put, that typically this is, some number over n, and we're sampling in the cyclic group n. So it might not be exactly n in the denominator, and then, as Mike just pointed out. So we go through, right, so after we have the superposition state, then we have to apply this black box, this u to the j. These are all the controlled u operations that were in the circuit diagram. And we may or may not be able to apply this efficiently. So this is something we really, I think, have to think about is, how to do this. And I think Matthias and Dave will present some work on how you can approximate this for different algorithms. In Shor's algorithm, for example, this is modular exponentiation. And then, so the output after we apply this black box is this superposition state here. Then we apply, as we saw, the inverse QFT, and we get out, a sampling of phi, which we're trying to approximate. So this is a general trick, phase estimation, that I think we'll hear about a lot during the next 2 days. So now I'm going to turn it over to Matthias.
Okay, thanks. And so I want to now tell you why we're meeting here, and the reason is that we want to turn the theory of this, the beautiful one, into application. Because once we build a quantum computer, then we want to use it to calculate something real. And so now we want to think about actually coding up something on a future machine. And then I don't like oracles, because I don't know how to build an oracle. I don't have it, I can't buy it. So we need to build this oracle. And I'm working in high performance computing, so I have to think about what I actually can compute on a machine. And then I'm running into problems. But first, I have the two jobs. One is I'm a professor of computational physics at the ETH in Zurich, and one day a week I work for Microsoft as a consultant on the quantum computing, and this is kind of a merger of those both aspects. So, what can quantum computers be used for? The first thing is factoring, that we know that can be done, in principle, if we build a big machine. The next thing, when you ask what else besides factoring would be interesting, and is simulating quantum systems, especially fermion systems, which are hard. And that has been around for 30 years, since Feynman mentioned it first, and many of you worked on this, and the proposed the algorithms. So, and we get an exponential speed up here, which is great, because we use quantum mechanics to evolve a quantum system. We get exponentially speed up in the memory, because we have qubits instead of classical bits, and so the Hilbert and so the wave function can be stored in the n qubits instead of 2 to the n the classical bits. And when we apply and the operator is also exponentially faster. So we have a huge speed up, which is good. But I've become cautious when talking to theoretical computer scientists. Just that an algorithm is in P does not mean I can ever compute it infinite time or in my lifetime. And so let's look what has to be done if we want to simulate the material. And let's look at the Coulomb Hamiltonian, the general one. We have the two-body term, we have the one-body term, so we have the one term with 4 operators and one with 2. And we want to time evolve it. And I don't have this oracle, so I have to build the oracle. And to build the oracle, I have to evolve it for some time. And I can do that by splitting the time into small time steps delta t. And I'm using the Trotter scheme to evolve it. And now, that's what we have to do. So what is the complexity? And this is a rough estimate. I have of the order of n to the 4 terms when I have n basis functions. When I run for time t, I have t over delta t Trotter steps. And for each application, I need of the order of 10 or so gate operations. The 10 is a lower bound. So this is roughly the complexity. And when I'm seeing n to the 4, then I'm getting scared. We know it's hard on classical machines. That's a big problem, but there one found ways of reducing it. For quantum machines, we also have something that we have to address. So let me now not focus on how I get the ground state wave function. Let me just focus on if I have a wave function, I want to get the energy or a gap or something. So let's just look at one aspect. I want to get this energy, and I do it by the phase estimation that Krysta has shown. And so I want to evolve it for a certain time or a certain power, and the time is the inverse of the accuracy that I need. So if I want 6 decimal places, I have to run for a time that's 2 pi times 10 to the 6 with small Trotter time steps. And now, what is the complexity of this? Is essentially I want to do about t over delta t times 10 times n to the 4, and I'm choosing an accuracy epsilon, so roughly this, and the Trotter time step, if we can choose one of 0.1, that's a big one, I think we can't go smaller. So then we're ending up at 10 to the 3 times n to the 4 over epsilon. Then, talking to people in chemistry, one want at least 6 digits. Many people say 10. Let's keep it to 6. Then with the complexity of 10 to the 9 times n to the 4. And now what is the runtime? If this is my algorithm. If an ion trap, currently the gate speeds are about 10 microseconds for an operation. In a superconducting qubit, one could aim for 10 nanoseconds. So let's assume we have a perfect decoherence-free quantum computer that operates at 100 megahertz. Then the runtime is 10 times n to the 4 seconds. We're going to run it for a month. Let's assume for a single run. So that's how many seconds we have and how many operations we can do. Then the biggest problem size we can do is 22 spin orbitals. I can do them in my laptop in a few minutes. We can do much bigger on a classical machine. So we have a problem in this simple-minded way. So let's be a bit more optimistic. Let's think we can speed it up and get a really good one that operates at a gigahertz. And I'm going to run it for a year. Then we can do 75 spin orbitals. We've beaten the classical machine. What it shows you, though, is that we have a problem. It's not just so simple as to say we can use a quantum computer and this efficient and polynomial time. Because just this oracle that Krysta mentioned, the time evolution of a quantum system. If we do it in a quantum system, like in this pen here, then it's efficient because it's analog. If we simulate it in digital hardware in a program, then we have n to the 4 scaling. So the question now is, what can we do? What important problems are there around that we can do if we build something that can do just a bit more than we can do classical? If we can do the full CI on maybe 60, 70 spin orbitals. So just a little bit bigger, is there a big problem here? And the second question is, we need new ideas to speed up those methods. In the simple-minded way, it will just be very, very hard. And so those are the two things that we want to discuss tomorrow then in detail. And first we want to hear our talks here about the state of the field and methods. And then we want to open the brainstorming of what one can do to make it useful. We have ideas, so it's not hopeless, but one should not just say we have a quantum computer and will solve all problems of quantum chemistry. It's not that easy if you want a real machine. So now, yeah.
I agree 100% with you. And I think it seems to me like the real space to make improvements is to determine what class of Hamiltonians can break the sort of Heisenberg time energy uncertainty.
Yeah.
So we know Shor's algorithm, if I just, instead of thinking about it number theoretically, I think of it as a Hamiltonian basis in time.
Yes.
I somehow can beat Heisenberg's time energy uncertainty, which is just a void, right?
Yeah.
So I'd be curious if people have a sense of like what chemistry Hamiltonians would fit into that category. They're not trivial.
That's one way of going. The other way is, can one simplify the Hamiltonians to get the scaling down? That's another way that one can go. You don't have to make it in one step or in a few, but you can find some that you can do faster than n to the 4. I think these could be two ways of proceeding.
Well, and there's this other thing that I talked to Matt Hastings a little bit about, which is sort of a look at an ensemble of initial states rather than a single initial state, and essentially don't try to simulate the entire system for a long period of time with the sequential performance constraints that implies, but instead do something much more clever about mixing between these states using a genetic algorithm approach or something else. This is like what we had with the Metropolis algorithm after all. I mean, the Metropolis algorithm is a very serial algorithm when you implement it the way Nick and the two tellers and so on did. But in fact, we have other techniques that don't rely on sequential simulation of the electron positions. And so, that might be a path.
Yes. So what we want to say essentially is that we need to think about new methods, and we should think broader, and the problem is not solved at the moment. Okay, but we have all day tomorrow for brainstorming, and these discussions were late already a bit for your talk, so let's start. Markus, thank you for coming here.
Okay. Well, I don't know. It's working. I hear it. Good morning, everybody. Yeah, my name is Markus Reiher. For those of you, which is most of you, who don't know me, I'm a quantum chemist, basically. So I work with standard many particle methods, which are solved on classical computers, to solve chemical problems. And I will actually come back to some of these problems which we had in your list in your first presentation. And I would like to discuss with you what are truly chemical problems. I mean, it's easy to say that, well, we would like to have dye-sensitized solar cells with certain properties and so on. I mean, let's look a bit more into the details here. And I happen to be here because I have been talking to Matthias for a few times in the past 6 months. And he already told me this story, which he just presented to you. Say, given there is a fixed, not too large number of qubits that you could use for quantum computing in chemistry, what chemical problems could you actually solve? And well, I will focus mostly on chemical reactions, hence the title. And most of these chemical reactions will have to do with catalysis, because this is kind of a problem which is really important in chemistry, and it's kind of, when you do stoichiometric reactions where you need an equal number of reactants in order to get a product, That is already a challenge, but it's even more challenging to come up with a molecule that can, you just need a few molecules in order to carry out a chemical reaction over and over again, meaning catalysis. And now let's work under the assumption that you have only, well, I call it here 100 one-electron states on which you could construct your quantum many-particle state. These 100 one-electron states I have in mind are actually molecular orbitals. These are not the qubits yet, because the molecular orbitals I'm talking about have 4 states. So it could be empty, a molecular orbital, spin up, spin down, and doubly occupied. So you would need 2 qubits in order to represent such a molecular orbital. So, and I just pick 100 to have one number which is, I would say, sufficiently large to be interesting for, to be competitive with standard methods on classical computers. Okay, and like I said, I will focus on chemical rather than physical-chemical problems. Right, so if you are physical-chemical problems are problems related to spectroscopy, so where you have some sort of spectrum that you would like to compute. Well, I'm after the chemistry. And the main target for us is the electronic energy, and that is defined by the Born-Oppenheimer approximation, so you have to solve the stationary electronic Schrödinger equation. Now, what would you need in order to describe catalytic reactions? So most of them, especially if they involve transition metal ions, I would say that you can set up a molecular model with 50 to 300 atoms. Okay, so you could do a huge deal of chemistry with such a model of 50 to 300 atoms. And this model you would then, depending on the chemistry you're doing, embed into some environment, and you would come up with an environment that is easy to model. For instance, a dielectric continuum, usually used to model solvents. You could use a quantum mechanical and quantum mechanical embedding, and for instance one option is to have a frozen density embedding where you take your active catalyst embedded and you embed it into the electronic density of some surrounding which is usually structured. And of course you have electrostatic embedding, and that's usually used in protein chemistry, and you can set up a force field, and into that force field you embed your quantum system.
Can I ask you a question?
Yeah, sure.
50 to 300 atoms, is each atom requiring 30 qubits to model because of its electronic states?
Yeah.
Okay.
I come to that point.
Please.
Before I come to it, let's look at this slide. So first of all, I mean, the nice point is for this kind of catalytic reactions, you can get away with a model with, say, 50 to 300 atoms. Could be much more, of course. We have chemical processes where you surely need more than 300 atoms. The nice... Can you explain that?
Why do you need 300 atoms? I just don't understand.
It's also on the slide. Give me a second. Before I tell you that, another important point to mention is that I would say that we get away, we don't need explicit nuclear dynamics. So what we can do is we look at stationary states at the Born-Oppenheimer potential energy surface. So you take a structure, and for a structure which is determined by the position of atomic nuclei, you solve the electronic structure problem and extract your chemistry from that. You don't need to move the nuclei around. For the reactions I'm interested in, of course, there are chemical problems where you need to do that, but for those problems I'm telling you about, we really don't need that. And these reactions, and that's the most important point, involve the breaking and forming of rather strong chemical bonds. So when you do that, this is when you get away with a model which has only a few hundred atoms. And what you do is you usually break only 1 or 2 atom-atom contacts at a time. Okay, this is why it's possible. Still, the problem is that you need to consider a huge number of nuclear configurations and a huge number of molecular structures. And well, for these nuclear configurations, you solve the electronic Schrödinger equation, and that also means that you also need to do for a molecule in different charge and spin states. Now, coming back to your question, say if you take 100 atoms, and this is a very low estimate, and each atom contributes 10 one-electron basis states, that would mean that you end up with 1,000 molecular orbitals in the end. And I told you we just want to use 100. So what can we do about this? That is a problem. The nice thing is that there are already ideas around for standard techniques to circumvent the problem. And that has to do with this active space concept that was basically developed by a group in Lund by Björn Roos. and his co-workers. And the idea is the following. I mean, you know that you have many more molecular orbitals than you can really treat already in a standard calculation. Now, why is it possible to select a reduced set of orbitals, which is totally sufficient in order to describe the chemistry? And this is called the complete active space concept. And so you select a few, or the most essential molecular orbitals, which are needed to represent the total state only in these active orbitals. Well, in the end, in these standard methods, you always end up with a kind of a superposition of many electron states, basis states, usually with a fixed number of electrons, and you expand your total state, your electronic wave functions, into this basis. And the basis is, of course, then constructed from those orbitals that you selected. Okay. Now, there are some drawbacks, of course, because, you select only a few orbitals, and that ultimately has consequences on accuracy. So usually you can make sure that you get qualitatively correct wave functions. Sometimes they are even quantitatively correct, because certain contributions might be lacking. And in quantum chemistry, we call them dynamical correlation. Also, it's not guaranteed that it will be possible to select the most relevant orbitals. But we will see that, say, 100 molecular orbitals is a reasonably good number for the catalytic processes I have in mind. A little bit more on notation. You will see this on the slides to come. QuArC means complete active space. So that is a set of molecular orbitals in which you construct your total state in an exact manner. And you have seen this on Matthias' slide before. We call that in quantum chemistry full configuration interaction, full CI. So to be more precise, full CI usually refers to the exact solution in a total set of one particle states. Since we restrict our set of one particle states, we call this exact solution QuArC CI if we do a full CI only within the active space that we have chosen. Now, since you do this restriction, you could also play around with relaxing the orbitals. And then when we do that, we call it QuArC SCF. So that's a QuArC CI method, a QuArC CI type wave function, where we also optimize the orbitals. Now, two examples that should illustrate what kind of chemical problems I do have in mind, which are important. One example is this one. It's not yet solved. Well, despite 50 years of research.
That's an ancient reaction, though.
Well, it's a very important one.
You bet.
So the point is the following. We have this in air, dinitrogen, molecular dinitrogen, 75%. In order to grow food, we need to transform it to ammonia. Usually it's done in industry through a process which is 100 years old. It's called the Haber-Bosch process, running at elevated temperature and elevated pressure. It consumes 2% of the annual energy production. And it would be nice to really convert dinitrogen under ambient conditions, so ambient temperature, ambient pressure, to ammonia. It has not been achieved by synthetic chemistry until the year 2003. And it is possible, though, because there's an enzyme doing this. Now, this is a system which first accomplished it in the lab. And it was published by the Schrock lab from MIT in 2003. And it works with molybdenum. You see here, this is I hope you are somehow used to chemical structures. So what you see here, this is well, if you want to solve a chemical problem, you need to get used to it. But of course, I explained this to you. So you see, there's a metal, this is the active center. It's a metal, it's a molybdenum atom surrounded by 4 nitrogen atoms. Then in the 5th position here, there's a dinitrogen ligand binding. So this comes from air. And then all of this here is a barbed wire of atoms taken from organic chemistry. It's basically a huge system. You see it in a ball and stick representation on the next slide. It's the first system to do say a few catalytic cycles. The turnover number is only 6. So say after 3 cycles, it drops dead. And that is very bad for a catalyst. You need to achieve 1,000,000 cycles, something like that. So we are in the position of a first system which is synthetic, which can do the job, but it's totally inefficient. And since 2003, nothing has changed. There's another system based on molybdenum available since 2 years, which can also do the job. It also drops dead after a few cycles, say 4. Okay? And of course you need an...
How does it break down?
Yeah, that we could study with quantum chemical methods. The point is, you provide electrons through these compounds here, and you have a proton source. And under these highly reductive conditions, what you do is you attach hydrogen atoms to these nitrogen atoms, and then the whole thing falls apart, because then it's no longer stable. And that's kind of the problem.
So, but there are nitrogen-fixing planets, right?
Yes.
So do they use, is it known?
The mechanism is unknown. The active site is known only basically since last year. It took 20 years to clarify how the active site is really composed. The mechanism is not yet solved, and one reason is actually that standard quantum chemical methods have problems here, for the reason that the number of active states that you could consider is too small. Of course, you can do DFT, but you never know how accurate that is. Yes?
Is it known how nitrogen-fixing bacteria work? Do they have...
No, this is what I just said. It's not known. It's
they have molybdenum?
Yes, they do, but it's believed that it takes place on iron. So the active site of this enzyme consists of 7 iron atoms and 1 molybdenum atom, and they are all bridged by sulfur. So in terms of selecting molecular orbitals, it's a mess.
I mean, these are not exotic planets, right?
No. No, this is, so for me the conclusion is that it can be done chemically, and so no, maybe this is also this is a true chemical problem, which I don't know how to solve algorithmically, because it's basically a combinatorial problem. The point is, you need to know where to place your atomic nuclei, right? That's what I said in the very beginning. We use the Born-Oppenheimer approximation, but if you don't have an experiment which really tells you where to put the nuclei, or from which nuclei the catalyst should be composed, well, there's not much that you can do. So, and this was the first system that could do the job, so everybody jumped on that system to understand how it works, but it's very hard and until now impossible to really improve. For instance, we substituted this barbed wire here of atoms, and whatever we did, it was worse than the original system. So this is a really hard problem. Well, this is a ball and stick representation of the catalyst. You see the molybdenum atom here in the center. These are in blue the nitrogen atoms. This is the N2 ligand binding. And here you see what I call this organic barbed wire, carbon atoms and hydrogen atoms. Well, we studied this system basically with DFT. This is the only method which is feasible actually, but it's not, we don't know anything about the accuracy. So having more accurate data would be really helpful here. It also tells you that you need to come up with structural models which incorporate the acid. This is the acid. Here you see the proton which is going to be transferred. That is actually a view on some of the reactions after the first ammonia molecule has been produced, because you see there's only 1 nitrogen atom missing here. And then you need to set up a molecular structure model. Well, we did it first with isolated molecules, and then we let the acid approach to 2 different reaction channels, which is depicted here. So that is what I mean with you need to consider really many calculations for different nuclear configurations. And this is just a glimpse of the full complexity of the process. It's something that calculations that we carried out within DFT, not knowing really what the accuracy is. Each node here is basically a different chemical species, and you see electrons are added, protons are added, and things are going on. And that's only for the system with the low turnover numbers, right? So this is just understanding what's going wrong. It's not yet the solution. So this is one of my major points here. Well, if you just run one calculation on one structure in chemical terms, it's pretty useless. I mean, you can solve a physical-chemical problem, but a chemical problem, no way. Well, what could you do with a quantum computer? Well, the point is there are certain essential steps in the mechanism. For instance, one of them is the exchange of ammonia, which is produced by the newly incoming dinitrogen ligand. And this is something that the Schrock system is really capable of doing. Many other systems are just dead. They produce ammonia, but ammonia poisons the catalyst, and then it sticks. You need to get rid of it and bind the new dinitrogen ligand. And this is something which is possible with the Schrock system. So in this kind of chemistry, there are only 4 essential steps which must be accomplished by a catalyst. You need to be able to bind dinitrogen, then you need to activate it, meaning you need to transfer the first electron, the first proton onto it. The rest is energetically downhill, you can forget about it. You need to get rid of the final ammonia molecule which is formed, and you need to increase the turnover number. So you need to deal with a huge amount of side reactions. And especially for the second step, a quantum computer could be helpful, because that is a step which involves electron and proton transfer, and it's very hard to model that within DFT. And I just show you one example, which is a different system for the same purpose, which would benefit from such a simulation. Here you see it's a dinuclear system. M stands for metal. The metal is ruthenium, could be iron. Then there's again an organic barbed wire, and the N2 molecule is clamped between the 2 metal fragments. The point is, you can transfer through reduction or photochemical activation an electron onto the N2 unit, and then you see that it will induce a structural change. And because of the structural change, protons will hop over to the dinitrogen ligand, and that would accomplish the important second step.
What is the spin state for N2?
Well, N2 is basically singlet, but the question is, what is the spin state of the metal fragment? So with respect to N2 as a molecular moiety, that's pretty harmless, but the metal fragment is a problem. For instance, if you have iron instead of ruthenium here, it's not clear what the spin state is. A second example, that is from the hydrogen production business for clean energy production, basically, as it is pursued with an enzyme, this time with the so-called iron-iron hydrogenase. And I'm not talking about this process of forming H2, because there are many systems which can do that. The point is, whenever you have such a system, it's sensitive to oxygen. So if you expose it to air, it drops dead. And you really need to do something about that. In biology, basically 3 different evolutionary independent enzymes are known which could do that, and that is the monoiron hydrogenase, the di-iron hydrogenase, and the nickel-iron hydrogenase. Except for this system, for all the others, the problem is O2 inhibition. In the left, for the system here on the left, you see here's the iron atom. The explanation is simple, it does not bind oxygen, but it has also a bias to split dihydrogen. So it's not the most efficient dihydrogen producing catalyst. Well, if you want to study this, well, you need to consider different reactive oxygen species, 3, 4, 5 of them. You have different pathways, different spin coupling scheme, different charges need to be considered. We did that also with DFT, and we considered more than 1,000 broken spin symmetry DFT calculations. And we don't know how accurate they are. The outcome was this. This is the most interesting system in terms of hydrogen production. The central site of iron-iron hydrogenase, Fe means of course an iron atom, S is the sulfur atom, and you see it has 6 iron sites. So 4 here and 2 in this subcluster over here. It's actually the subcluster which binds molecular oxygen from air, for instance, and then it produces reactive oxygen species which are converted to an OOH radical and to this H2O2 oxidizing molecule. And these reactive oxygen species, then they attack the cluster and then it decomposes. And that's the reason why it drops dead. And from DFT, these are the energies for the process. We don't know how accurate that is. All we know is that this is pretty much in line with what is experimentally seen, but we have no other independent way to test that, and for this it would be nice to run calculations on a computer which could treat 100 molecular orbitals. And of course, if you understand that, then the next thing is you would increase your atomic model, say, to 700 atoms, because what you can do then is mutagenesis studies. So you can change the environment in order to make it more oxygen stable. Actually, this is something we are working also on, and in collaboration with experimental people who could do 600 mutants per day. Okay? Although they can do 600 mutants of the enzyme per day, the combinatorial possibilities here are so large that you really need theoretical calculations in order to guide you. Okay.
Sorry to interrupt, but my impression for this sort of work is that, in some sense, the experimentalists feel like the calculations are almost good enough, right? You say you have a space of a gazillion. You give them, say, 10,000 things that look good to you. They make 600 mutants. Of those, 20 work, right? And I hear theorists talk a lot about how it would be great if we could do something better. But the experimentalists are always like, look, we got these 1,000 things, we tried 600 of them.
It's true.
It was great.
Yeah, that's true.
So what do you tell your experimental colleagues to get
Raise your standards.
Well, what you're describing is pretty much what's going on in the drug design industry. Because the experimentalists don't care whether this or that proposition would be right or wrong, just to nail down the millions to a few thousand, and those are then tested experimentally. Well, I think when it comes to catalysis, you need to change the structure of the catalyst. And in order to do that reliably, you really need a high accuracy, because it might be very hard to synthesize the guy. And it could take a year or two until you have figured out how to do that. And when you're in such a situation, you really need to be able to trust your calculations. And well, DFT could work, but you never know. Okay, but this is as much about the two examples as I wanted to tell you, just to give you an impression what a chemical problem really is. And of course, there are also molecular properties we are interested in, and one property that we have spent some time on calculating is actually the spin density, because that turned out to be very hard with standard methods. Why is that so? Well, let me explain to you. What you see here are basically spin density distributions calculated with different standard methods. All are QuArC calculations for a triatomic molecule, and you don't see the atoms. There's an iron atom here, and there's a nitrogen atom here, and an oxygen there. So it's FeNO. And then the notation is as this. 7 means 7 electrons, and this other second 7 means in 7 molecular orbitals. Then this means 11 electrons in 9 molecular orbitals, and so on. So this directly relates to the question, how many molecular orbitals could you treat with the standard method? The point is, with the standard method QuArC, you can treat at most, I would say, 18 electrons in 18 orbitals. So this is why if you could treat 100 orbitals, would be great, or even 50. Here, you clearly have a problem, because you see this, well, the point is this is the spin density, and all these representations are spin density differences, to be more accurate in my description. And you see that the spin density kind of oscillates around the reference density, which I just picked as a Cas11 in 14 reference. But we could go to other algorithms which are kind of not yet standard in chemistry, although they are quite standard in physics, and like DMRG, the density matrix renormalization group, because with DMRG we can really treat larger active spaces. Here you see just one slide which should convince you that we can really converge a spin density within DMRG, say for 13 electrons in 29 molecular orbitals. And then the reference spin density which we produce is this one. Now we can use that in order to compare with QuArC and DFT, just to see how wrong it is. This is the comparison with QuArC. So these are not the spin densities, but spin density differences. I forgot to tell you that let me go back. So this is the spin density, and blue means alpha spin excess, and yellow means beta spin excess. But these are spin density differences. And you see that the QuArC calculations with this small number of active orbitals, 13, 14, 15, 16, is too much off. Right? So this is the error in the spin density with one of the standard methods, QuArC in quantum chemistry.
What's the catalyst that
1% error, 10% error, 100% error?
But it's an isosurface, and I don't recall in absolute terms, but the error is too large. It's of course in the paper if you want to look it up. You can also take the difference to the DFT spin densities, and this is for 8 standard density functionals which are used in quantum chemistry, and well, they look like spin densities, but this is the error in DFT. Okay. We can do that for larger systems. Before I showed you a triatomic model system. Here we have a full-fledged transition metal complex. In order to describe the spin density here, you need, for instance, 13 electrons in 43 orbitals. It also tells you if you can treat 50 molecular orbitals, meaning 100 spin orbitals. Well, with respect to the spin density, this is a system you could study. The spin density is, of course, important for certain spectroscopic techniques in chemistry. Now, the final point I would like to discuss with you is, well, is there a way to choose the molecular orbitals from the huge set of molecular orbitals that you need to describe, that you need for the description of your molecule? I mean, is there an automatic way to determine those orbitals which are relevant to the active space? And usually that is done based on energetic criteria and mostly, I would say, on chemical intuition. But recently it turned out that concepts from quantum information theory are quite beneficial here. And the concepts that we studied are the single orbital entropy and the mutual information. The single orbital entropy is computed from the eigenvalues, omega, of the reduced density matrix that we obtain when we trace out all the environment states with which a single orbital would interact. And then we end up with a 4x4 reduced density matrix, and we have 4 eigenvalues, and we can compute the single orbital entropy here. And in order to understand what the entanglement between 2 orbitals is, we could calculate the mutual information. These concepts, by the way, have been introduced by Legesar almost 10 years ago, and the mutual information by Rissler, Nowak, and White in Chemical Physics 2006. So the mutual information is computed from the single orbital entropies and from the 2 orbital entropy, which you get in the pretty same way by using the eigenvalues of the 2 orbital reduced density matrix, so where you consider 2 orbitals explicitly and you trace out all the environment orbitals. Now, we can study these concepts, and it turns out that we usually see 3 subsets of orbitals with high entanglement, medium entanglement, and weak entanglement. And it turns out that they pretty much match the chemical intuition. So in chemistry, people have used to, for instance, if you have active electrons in pi orbitals, you should correlate them with anti-bonding, so-called pi star orbitals, and so on. So we have kind of a measure in our hands that we can replace chemical intuition here, which is really good if you want to pick, say, 100 orbitals from the set of 1000 that I had on one of my slides. And well, I could go in more detail here, but the pattern in all the molecules that we have studied so far is pretty much the same, where you always have these 3 classes of orbitals when it comes to orbital interactions. And we have seen that also for larger systems. That's basically everything I wanted to tell you about. So my conclusion here is the following. I think it is possible to define important yet unsolved chemical problems that would benefit from the availability of a quantum computer if it could treat 100 molecular orbitals. If it's only 50 molecular orbitals, well, I don't know whether it's worth the effort. It's important to know that whenever you do such a quantum simulation, you must be able to beat all the standard methods that are around, like coupled cluster, QuaSCF, perturbation on top of QuaSCF, DMRG or DFT. And I was also asked in this email by Leanne to put up some questions. Well, these are a few questions that I would have, because some of it might be already answered by Matthias' slide. So if you have this problem, how fast could it be solved on a quantum computer? Would it be really more efficient than the existing schemes? Would it be possible to include what we call the dynamic correlation effect? So the fact that we have omitted most of the orbitals in the calculation actually. And how difficult would it be to compute molecular properties, response properties? But that's it. Thanks for your attention.
Are there more questions? We have time for discussion now. Mike?
Yeah, so you described how information concepts like entropy and mutual entropy can be used to select the most important orbitals to keep track of. But often classically, when you're studying degrees of freedom, you settle on linear combinations of the initial degrees of freedom, so not just choosing the best ones from the original basis. By some principal value method, for example, you select the largest principal values and keep those.
Yeah.
So I'm wondering whether something analogous is possible. Could you select linear combinations of
you can do that.
orbitals?
In fact, I was thinking about taking combinations of orbitals and occupancies. I mean, actually, don't move the electrons one at a time either. Suppose you could say, okay, there are these quantum mechanical transitions described by unitaries among this, let's call it a basis for a minute, of occupancies in sets of orbitals. And what we seek is a combination of those guys that we can model. I have no idea if that would work, but I mean, that's the kind of, that extends not only the basis to the linear algebra, but also gets around this pushing one electron at a time game that we do.
Yeah, well, there's a lot of literature and knowledge available on how to choose these one-particle states. And the point, I didn't talk about this because I considered it not to be a problem because there is already this knowledge available. For instance, you could pick the molecular orbitals that come out of a Hartree-Fock calculation. But that is not what we did here. What we did is we used so-called natural orbitals that we computed from a small QuArC-SCF calculation. So we run a QuArC-SCF calculation which also optimizes the orbitals. And then we pick that linear combination which diagonalizes the first order density matrix.
So this is already done.
Yeah, that's why I didn't talk about it.
I see. Okay.
So I'm confused. It seems like this procedure, choosing the large orbitals, requires you to solve the bigger system already. If you're going to choose the orbitals this way, you've got to be able to trace out everything else. So it seems like you've already solved the system here.
Yeah, that's right. The point is, what we did here is we ran small DMIG calculations. Small in a sense that with a limited number of iterations. I think it's not a principal problem that you get this information a posteriori. You could come up with a scheme to sample that knowledge in advance, I think. But in any case, it will be good to have such a measure which tells you whether you picked the right orbitals. Even if, for instance, this can be done only after the quantum computation. But I don't think that's true. You could get that knowledge before, with standard methods, for instance.
So you're saying 100 orbitals is what we need at least. When you get up to 50, then it's very hard to find.
If you want to be competitive, I don't know whether, I guess Garnet agrees, don't you?
Yeah. I mean, in the language that you were saying, these are only the 100 important orbitals.
Yes.
I mean, underlying there are thousands of orbitals, but.
So then, if nobody, this increase here, then that has the scale that we have to aim for.
When it comes to chemistry.
Yeah, for chemistry, yeah.
So you identified a couple of really practical targets, like functionality of the catalyst, and then you looked at the theory. But what about new spectroscopic techniques or new measurement techniques that could probe these things more directly? I mean, if you think of not of quantum computation on the theoretical end, but think about the experimental techniques that people are developing, it may very well be easier to use, say, tricks that would let you do all these complicated gates to directly probe input systems. I mean, think about the sort of ultra-fast spectroscopy measurements that people have done in the last 5 years. as an example of that.
So I don't get your point. So in order to solve the chemical problem, or to replace kind of the universal quantum computer by a system which just simulates directly?
No, I'm not talking about simulation, I'm talking about experiment now.
Yeah.
So could you take techniques out of experimental quantum computation and use them to more directly probe chemical systems? I guess...
Can I ask you a question here?
Sure.
So take these biological enzyme catalysts, right? So we know people do these DFT calculations. A couple of things don't happen. One is they don't fold the right way, so there's a huge hole, and all this water comes in and kills the catalyst. The other thing which goes wrong is somehow, in some sense, the redox activity of the active site is reduced for some reason. There's some histidine or whatever which is screwed up. So I think what do you see as like the chemical, like the physical properties of these things that make them good catalysts? Like, what do I need to worry about? Do I need to worry about redox potential? Do I need to worry about sort of the cooperativity of the surrounding?
And the point is that you need to figure out.
Yeah, but so Peter's question is, can we use our ability to do coherent spectroscopy
How would you
as
do
a way to like test?
How would you do that? I mean, maybe I don't get you're right, but the point is, in theory, you could study a system which is not yet there experimentally. So how would you do that with an experiment? You see what I mean?
Yeah, but I think.
Well, let me ask the question another way, which is if you could order experimentalists to do whatever you want, what experiments would you ask them to do? What things would you ask them to measure that would best inform the calculations?
To figure out whether the calculations are correct or not. Okay. Well, actually, what you really need in the first place is structures. So I don't think that you really need new experimental techniques. The point is, it's very difficult to get the structures because you need to. Well, if you use X-ray diffraction, you need a crystal. Difficult to get for certain systems. You could use more indirect techniques, and of course, that's why I basically had this point here, molecular properties. Of course, with standard techniques, we can compute molecular properties. For instance, for whether you have N2 binding or not, vibrational spectroscopy is sufficient because it tells you where the vibrational stretching vibration of N2 is. It's perfect. So I don't think that there are new techniques in spectroscopy that we really need. These systems are very difficult to treat experimentally, and that is basically a chance for us, in theory, to really compete on an equal level with them.
Yeah. Okay, thank you. Markus?